You've been told that only square matrices have inverses. That's true, but it's not the whole story. Take a tall, skinny rectangular matrix. It has too many rows for a normal inverse, yet a matrix placed on its left can still produce the identity. The same trick fails on the right. To see why, look at the two ways a rectangular matrix can be as good as invertible. A square full rank matrix has a clean two-sided inverse. Multiply on either side and you get the identity. Rectangular matrices split into two cases. A tall matrix has more rows than columns and a full column rank, where the rank R equals n. A wide matrix has more columns than rows and a full row rank, where the rank R equals m. Each case hands us a one-sided inverse, but only one side. Let's start with the tall case. Matrix A has m rows and n columns with m greater than n, and it has full column rank, R equals n. Because the columns are independent, the null space contains only the zero vector. That means the equation ax equals b has either zero solutions or exactly one solution. Now here's the crucial fact. Form A transpose times A, tracking the dimensions, an m by m matrix times an m by n matrix gives an m by n result. So this is square. It is symmetric since transposing A transpose A gives back A transpose A itself. And with independent columns, it is invertible. We call A transpose A the grand matrix, and its invertibility is the key that unlocks everything that follows. Since A transpose A is invertible, we can write down this matrix, a transpose A or inverse, times A transpose. Now multiply it onto A on the right. Group the parentheses so that we have A transpose A inverse times the quantity A transpose A. Those two factors cancel, leaving the identity. So this expression is a left inverse of A. Let's check the dimensions. It's n by m times m by n, which gives an m by n identity. Now take a concrete example. Let A have the rows 1, 0, then 0, 1, then 1, 1. Then A transpose A works out to 2, 1, 1, 2. Its determinant is 3. So the inverse is 1/3 times the matrix 2 minus 1, minus 1, 2. Finally, multiply A transpose A inverse times A transpose times A, and you get the 2 by 2 identity exactly. The left inverse works. Now push it one step further. What about the other side? Try the same kind of matrix on the right. To do that, you would need the product A times A transpose to be invertible. But here's the problem. A times A transpose is an m by m matrix, while its rank is only n and n is less than m. A bigger matrix carrying too little rank simply cannot be invertible. So in the tall case, no right inverse exists. The deeper reason is this. A rectangular matrix can never be inverted from both sides because either A or A transpose always has a non-trivial null space. Something always gets collapsed, and you cannot undo a collapse from both directions. Now mirror everything from the tall case. Consider the wide case. More columns than rows, so n is greater than m, and the matrix has full row rank, R equals m. Because the rows are independent, the equation Ax equals b always has a solution, but infinitely many of them, with n minus m free variables. This time is A times A transpose, that is the invertible one. It is m by m, symmetric, and full rank, so the right inverse is A transpose times the inverse of A times A transpose. To check it, multiply A onto its left. A times A transpose times the inverse of A times A transpose. The A times A transpose and its inverse cancel, leaving the identity. For a concrete example, take A with rows 1, 0, 1, and 0, 1, 1. Then A times a transpose is again 2, 1 on top of 1, 2, and A times the right inverse gives the 2 by 2 identity. Now here's the part nobody warns you about. Go back to the tall case and take the exact same pieces of the left inverse, but multiply them in the opposite order. Write capital A times the inverse of A transpose A times A transpose. Call this capital P. This is not the identity. Let's compute it for our matrix. Recall that the inverse of A transpose A equals 1/3 times the matrix 2, minus 1, minus 1, 2. First multiply capital A on the left. That gives the 3 by 2 matrix. 2/3, minus 1/3, minus 1/3, 2/3, 1/3, 1/3. Now multiply A transpose on the right. The result is a 3 by 3 matrix. 2/3, minus 1/3, 1/3, minus 1/3, 2/3, 1/3, 1/3, 1/3, 2/3. That's clearly not the identity, but check two things. First, it's symmetric. Second, squaring it gives back itself. P squared equals P. This capital P is a projection matrix. What does P actually do? It projects onto the column space of A. Picture a three-dimensional space with a two-dimensional plane inside it, the column space. Take a vector B sitting off that plane. P drops B straight down perpendicularly onto the plane. That landing point is P times B. So P acts as the identity for any vector already in the plane, and it kills the part sticking out perpendicular. The matrix was asked to be the identity, but given an impossible job, since it cannot reach all of three-dimensional space, it does the best possible thing. The identity inside the column space and the zero outside it. This isn't a curiosity, it's the heart of least squares. When the equation ax equals b has no exact solution, an overdetermined system with more equations than unknowns, you want the closest thing you can get. The normal equations are A transpose A times x hat equals A transpose B. And there's our grand matrix again, A transpose A, exactly the coefficient matrix that's invertible in the full column rank case. Solving gives x hat equals the inverse of A transpose A times A transpose B, and A times x hat equals A times the inverse of A transpose A times A transpose times B, which is exactly P times B, the projection of B onto the column space. So the projection finds the best approximate solution. The closest reachable point to an unsolvable demand is precisely what P delivers. Step back and see the symmetry. Full column rank gives a left inverse built from A transpose A. Quantity A transpose A inverse times A transpose times A collapses to A transpose A inverse times A transpose A, which is the identity. Full row rank gives a right inverse built from A times A transpose. Here A times A transpose times the quantity A transpose inverse again collapses to the identity. So when the pieces meet in the correct order, they deliver the identity. But put them in the wrong order and something different appears. A times the quantity A transpose A inverse times A transpose is the projection matrix P, and P squared equals P, the hallmark of a projection. One-sided inverses and projections are two faces of the same construction. These projections will return everywhere, from regression to orthogonalization. Same pieces, different order, profoundly different meaning.